Shortest night path. Now, this one took me on a bit of a journey. So I started with an ordinary kind of solution, which was kind of a breadth first search, tree exploration algorithm kind of thing, which is the normal kind of approach you take for this kind of a problem. But I couldn't shake the nagging feeling that there was some more mathematical performant version of this where you could calculate the path between two positions on a chessboard that a knight can take. So just a really quick overview of the problem. So given two positions on a chessboard, find the least number of moves that it would take a knight to get from one square to the other square. So an example, if your knight started on a3 and the destination is b5, then that would be one knight move. Because let's just plonk a knight on a3. It's one move. But if you had to get to c3, you'd have to then do two moves. So the result would be two. I solved it initially with a breadth first search algorithm, which I'll try to concisely go over in a moment. But then I used that solution to generate some data to then import into Excel, and it gave me a lens with which to view how it could be mathematically computed. And in doing so, I managed to create a two-line solution, complicated two-line solution, but a two-line solution nonetheless, which is much more efficient and performant because it calculates the answer rather than doing a tree exploration approach. So I'll be going into that. I thought I'd share a little teaser before we get into it of where I'm heading. So this is the two-line solution I mentioned before. Lots of kind of mathematical stuff going on in there. Juicy things to unpack that I can't wait to talk about. And I quite enjoy how much shorter it is than like literally all the other solutions. There is one that I found actually that is very short, but it's just brute forcing the answers. So that doesn't count, right? Mine will in fact work on an infinite chessboard. So there, put that in your pipe and smoke it. This one's pretty good. But this is essentially breadth first search. Similar to mine, just more concisely written. So yeah, on with my one. Okay, so I've got a version of my solution here, which is using breadth first search. So what we have is a bunch of utility functions at the top. So worth noting that in the input that we get to our function here is the chess notation. So it's helpful to map between that and coordinates. Just so we can manipulate the coordinates a bit more easily than we can the chess notation. So I've got two utility functions here for converting from, say, A3 to X and Y coordinates here. The way that that works is it's interpreting the string part or the first character, so this A through H, as a base 18 number. So kind of the way that hexadecimal might convert into a number. This is using base 18, goes all the way up to H. And then we're deducting 10 because the A through H range would be 10 through 17. So if we deduct 10, it gives us 0 through 7. So that's quite a handy thing to do. And then this is just a case of taking the number that we get at the end and deducting 1 from that to convert it from a 1 to 8 range to a 0 to 7 range. So we've got one here to convert back from the coordinate back into the notation. So literally just taking the relevant letter from this string based on the x coordinate, and then it's just y plus 1 to convert back from 0 to 7 to a 1 to 8 range. Okay, so in tree exploration algorithms, AI topics in general, there's the concept of a successor function. So a successor function takes the a given known initial state and then will produce a set of possible resulting states from that initial state. So in the case of a chessboard, you might pass it the initial state of the position of a knight on the chessboard. And the successor function will then return back to you the possible places that the knight could move from that given initial state. So we'll pass it an initial state, which is a single location, and then it will return back to us 8 locations. Of course, at the edge of the board, it could be less than 8. So yeah, that's the purpose of the successor function. And I've got a function here, which is my main successor function that I'm calling. It accepts notation and converts from the notation into a coordinate, which then calls this function. And we get that coordinate. I've then just got an array of offset values to map to the new location that the knight might end up in. And I'm mapping through all of those and then filtering out the ones that end up off the board, essentially, by checking for a value that is greater than 0, greater than or equal to 0, and less than 8. So this then will map over those and map the coordinates back into chess notation. It's quite handy dealing with chess notation for a reason that I'll go into in a moment when I show you the actual version that I produced compared with this different version that I'm showing at the moment. So now that we've got this successor function, I can go into the algorithm itself, which is implementing the breadth first search. So we start off with a fringe array. Now, a fringe is a term that's commonly used to represent the boundary between the known territory and the unknown territory. So it's the fringe of what we know. And in the fringe, we initially populate it with the start square, because that's one thing that we know. Just set this moves to 0, and each iteration where we move an additional, make an additional move with the knight, I'm just incrementing the moves variable by 1. So on each iteration then, we take the known places, and I'm just iterating over them to gather the successors from that initial state. So given we started at A3, let's put that here, it's going to return back to us all of those squares. And it's going to populate that in this fringe. So the next thing that we do in the algorithm, it's really quite simple. We check, did we find the end square? Have we found the end position? If yes, then we return the number of moves that it took to get there. If not, then we iterate again, and we've updated the fringe to contain the new locations that we found, and we just iterate again until we've explored the entire board, and at some point we're going to hit the target square that is the finish. So that's a simplified version of what is the actual solution. The reason this doesn't work is something I can demonstrate now. If I run an attempt, essentially the code is not efficient enough because there's so many different routes that the knight can take. You know, there's nothing in our code that stops us from just hopping all over the place. So it's going to, after the first iteration, we're going to go, oh wow, I can use different colors. That's actually quite handy. So after one iteration, we're going to be going to where the green arrows point. But after 2 iterations, actually, how did I even do a color? Hold control. Yeah, after 2 iterations, we're going to have all these possible places. And that's going to be stored in our fringe array. This is going to take ages if I do all of these, but you get the idea. Now, after 3 iterations, we can have all of those plus another iteration. So it's just growing exponentially. And as a result, although most of these pass, in fact, all of them pass up to a point where we've just timed out the tests. It's not completing fast enough. So for that reason, we have to introduce something that just keeps track of where we've been. Because if we go here and then we go back here again, we've already seen this square. So we don't actually need to process it again, because any path that ultimately leads back to this square is going to be a longer path than, yeah, it's just not going to be an optimal path, because what's the point of going around in a circle? I've just copy and pasted in the final version of the breadth first search that I used, and it's essentially the same, except for I have here a set which keeps track of the places where we've been. So I've called it scene, and I've populated it with the start. And here, instead of reassigning the fringe variable, I'm setting it to suit a list of successes. And doing the same thing, if the successes contain the finish, then we return the number of moves that it took to get to that point. Otherwise, we take the successes array and we filter that array by the things that we've seen before. And we only populate the fringe with the things that we haven't seen. And then finally, we just ensure that we populate the scene set with the things that we found when we called the successes function, so that we update the things that we've seen. Now, this version works pretty much exactly the same. However, it no longer will process repeatedly the same thing that we've seen before. So let's see how it works. And hurrah, it works. It's just quite a nice little algorithm. I quite enjoy writing tree exploration algorithms, and this is a pretty classical example of a breadth first search. Just in case you weren't aware, the reason why it's called breadth first search is because we traverse a tree such as this in this kind of an order, i.e. we go along the breadth first. And depth first would be traversing the tree by exploring more deeply. We go back to here, and then here, then go back up to here again, and then 5, 6, 7. So it would traverse the tree in that sort of a manner. So with depth first search, this is clearly a problem if we happen to find a path that goes in a circle, because we're going to just keep traversing this tree forever. So yeah, don't do that. So yeah, that's why breadth first search is more suitable, because we're going to just keep exploring the boundary further, especially if we keep track of where we've been. I guess depth first search would eventually get to the final position, assuming we're keeping track of the places we've been. However, there would be no guarantee that it is in fact the shortest path, because it could do something weird like this, only to get back to this square where you could have taken a shorter path. I could not, for the life of me, shake the intuition that this could be solved without a tree, without exploring routes to the night, and whether you could calculate the difference in some manner. For example, you can calculate the distance between these nights with just Pythagoras. And the distance, so I suppose if it wasn't for the irregularity of the movement of a knight, calculating the number of moves that the piece would take would be easy to express as some kind of proportion of this distance. So I wanted a way to visualize how many moves each square on the chessboard would take. So I started thinking about an infinite chessboard. Well, if I had a knight in the center and then an infinite chessboard, you could plot on that chessboard the number of, or the minimum number of moves that it would take for a knight to get to a given square. So I thought, hey, I wonder what that looks like. You could do like a heat map or something and see just what it looks like visually. So that's what I did. The approach that I took to generate the data was to just repurpose this breadth first search algorithm that I've already created. So I'm going to be generating it for a 40 by 40 board. And for that reason, I'm using a different key rather than the chess notation because I don't have 40 letters. I'm just using comma separated X and Y values here for the key. Now you'll notice I'm using a map now instead of a set because I want to both keep track of the fact that we've seen the square and I want to keep track of how many steps it took to get to that square. So for the initial position, which will be 2020 on this 40 by 40 grid, I'm going to set that to 0 steps because we haven't moved yet. Populate that into the fringe. And the algorithm works essentially exactly the same as it did before, except I've removed where I have an escape. So I'm not actually going to return when we reach some square. It's just going to propagate the algorithm throughout the entire board and populate that scene map. And just collapse these, come to those later. And yeah, it's just adding the number of moves that it took to get to the successor. Each time we see something new, it's just going to capture the number of moves that it took to get there. Finally, just going to keep iterating until the fringe has been exhausted, so there's no more potential places to explore, or we've taken too many moves just to protect against infinite loops, which doesn't happen in this version of the code, but I may have made that happen before. Then finally, it's just a matter of outputting the data. So just concatenating it all together with comma separated values and printing it on multiple lines so that I can copy and paste it into Excel. So I will do that now. Rather obviously, the further away from the origin you are, the greater the number of knight moves that it takes to get there. But there's also this interweaving of alternating numbers that isn't immediately obvious how it works. Because this, I don't know, take this row here. So it goes 7, 8, 7, 8, 7, 8, 7, 8, and then you think you understand it. It goes 8, 9. Then you've got 8, 9, 10, and it's a bit weird. And upon inspection, after a while of staring at it, it's apparent that you've got these kind of segments that have different behavior. So if you look at this kind of area, you've got these sevens all in a row, and then you've got eights, and then you've got nines. But then that behavior stops when you get out here because you've got 9, 9, 9, 9, 9, and then 11 again. So it's quite weird how it behaves. Sort of makes sense intuitively, I guess, but it isn't immediately obvious looking at this version of the diagram. So I had an idea. There's a lot of the weird patterns seem to come from something that a phrase I made up. I don't know if it's a real phrase, local chaos. So I was thinking, well, it's pretty chaotic that the immediately adjacent square takes 3 moves to get there. I mean, it's understandable if you know how a knight moves, but that's quite exceptional when considering the distance. I mean, it's literally the closest square, and it takes 3 moves to get there. So I was thinking, well, that local chaos is probably responsible for the irregularity that we see and these patterns that we see. So I was trying to think of a way, how could you get rid of that local chaos? And I came up with the idea that let's just say you had 9 knights and you could just choose which one was going to be your original knight. And I wondered what that would look like if we went with that. So I generated the data for that. Now, in terms of my algorithm, it's quite easy actually to generate that data. So it's just a matter of claiming that we've seen all of the adjacent squares and populating the fringe with an initial array there is a knight on all of those central squares. So that's the change that I made, and I will run that now. And with that change made, this is what it now looks like. Quite a lot more understandable. We just have these concentric circles, and it's quite fascinating to inspect. Again, you can see the quadrants. So if you drew a line through this kind of corner, you've got rows, and then here you've got the same thing, but just diagonal. Then columns, diagonal, rows. So that's a much more understandable pattern. So how's this going to help us? Well, I had one more idea about how I could visualize the data. And I thought, well, what if you subtracted one of these from the other? So you've got the complicated version, you've got the simpler version, which accounts for this local chaos idea that I thought about. And then if you deduct one from the other, you can see the difference between the chaotic version and the non-chaotic version and see if there's any patterns in that. So I'll just take this here and do this square minus this square and drag that little baby across. Drag it down. Oops, bit too far. And now look what we get. Again, quite hard to digest, but you can see a repeating pattern now. Well, it was repeating before, but to me, this made it a little more obvious. You have some weird chaotic behavior when you're close to the origin still, some exceptions. But beyond that, it follows a pretty regular pattern. Something else I did to help try and understand the behavior was to play with the lengths of the legs of a knight. So you've got a 2 and then a 1. Makes an L shape. Now, if you had an L shape where the longer distance was much longer, what would this look like? So that's why in this section here, where I'm calculating the successes, I'm now using variables rather than hard-coded values, so that I could play with different distances. So with the long side being 10 and the short side remaining as 1, this is what it looks like. Now, doing this really exaggerates the idea of this local chaos that I was talking about. So here, it takes 11 moves to get to the adjacent square. And to get to the adjacent square of that square, it takes 18 moves. It's quite crazy, really. But you can follow the path. If you go here, and you can follow the logic as well. So if you think about odd and even numbers, so if we want to move up by 1, that's impossible to achieve by any even step. Therefore, moving in the long direction is not going to be an option at all for this step of just 1. So in order to achieve that distance, we have to move in a horizontal direction in order to use that 1 distance. But that puts us really far away from the origin. So that is why that adjacent square is so hard to get to, because we have to move all the way over here and then kind of zigzag our way back again. 7, 8, 9, 10, 11, which I thought was really interesting. That gives us some insight into why that local chaos occurs. And the effect of that would be reduced, I think, by being far from the origin, because, you could, in your route to that faraway location, you could just sneak in one of these like lateral moves. So moved was I to come up with a solution that I busted out my Visual Basic for application skills from long ago and added some macros to a workbook to just make it easier to visualize the route back to the origin. So if you assume this is the origin, the red numbers indicate the path that the knight would take to get back to the origin. So this just helps us to visualize how this works, and it becomes a bit more obvious what's happening. Now, if I go over to here, alongside doing this, I was trying to mathematically calculate on pen and paper a method for calculating the number of moves, but that turned out to be pretty hard as well. But I was thinking along the lines that in order to get to a given position, it's going to be a number of moves, and in the X direction and in the Y direction, you could express that number of moves as a sum of twos and ones. And I played with that idea for a little bit, and that was pretty hard. I've thrown away the piece of paper that I'd scrawled on. But playing with this also it indicates a similar kind of idea. So if I go along this X axis, here you can see that the knight has moved always in the long direction. But if I move one more square, because of the reason I mentioned before about if I move by one, I can't move two squares in the long direction of the knight using the full length of the piece move. It has to do some kind of kink. So whereas before this is 4 twos, 2, 4, 6, 8 in terms of squares moved, if I move one more, it's 2, 4, 6, 8, and then a 1. So along that x-axis, you can express that as the sum of the distances that the knight moves. That kind of makes sense. And then moving by one more. Now, this is interesting because if I select the square above, you can see that that's an exact round number again. It's 2, 4, 6, 8, and then 10 squares moved, which therefore is 5 knight moves. But because I'm I'm down here, because of that local chaos idea, we're adjacent. It must therefore be 2, 4, 6, 8. So 4 lots of 2, and then 2 ones, and then it's 4 twos and 3 ones, and then finally it bumps up to 6 twos again. So doing that one more time, you've got 6 twos and a 1. 6 twos and then 2 ones, 6 twos and then 3 ones, and then finally 1, 2, 3, 4, 5, 6, 7, 8 twos. So it follows a cyclical pattern. Now, what I basically did next was go through all of the scenarios on several tabs, just taking examples like that and calculating an algorithm or a mathematical expression to get to that cell. Having a quick glance at this again, I mentioned before there's these little zones of repeating patterns. Now I've extracted the relevant zones. Here you have this and you have this. And they are mirror images all around this whole kind of diagram. So you get this repeated in all of the corners and you get this repeated in all of the edges. And of course, we've got this kind of local chaos zone that I identified that has some exceptions within it. So of course, these sections that I've highlighted here and here that are repeated around the board are themselves have a line of symmetry down the center as well. So actually the key segment is this triangle. And if we're below this line, then it's one type of pattern. And if we're above this line, then we're a different kind of pattern. And just to call out straight away, that line that gradient of 0.5 is why I've got this ternary here. So if dy over dx is less than or equal to 0.5, then we calculate one kind of an expression. Otherwise, we calculate a different kind of an expression. This one is quite a lot simpler than the other one because, well, it just looks a lot simpler, I suppose. You can see these stripes. And effectively, if you calculate the distance in terms of the Manhattan distance, so the number of squares that it takes to get to a given position, it just increases by one each time. One, yeah, so you got 0, 1, 2, 0, 1, 2. As you get further and further away, it's always 0, 1, 2, 0, 1, 2. So that's why we're using the modulo 3 in here. So you're calculating the distance. I should back up actually. I've got some code here that does parseInt. So I'm parsing the input as before with breadth first search and mapping that to x and y coordinates for both the start and the finish x and y. I'm then taking one from the other so that I calculate the deflection in the x-axis, deflection in the y-axis for the start and the finish. So I get the distance, and then that becomes relevant down here. So the dy plus dx divided by 3 gives us the number of steps that it took. If I just go up to the non-diff version, it's really hard to explain this stuff. It took me ages to figure all this out. But yeah, in essence, it's the distance divided by 3, which kind of makes sense if you think that the distance that a knight travels is 3 squares. So it's 3 squares in distance plus the modulo 3 of whatever that distance is. Yeah, so that captures the fact that it's this 0, 1, 2, 3, 0, 1, 2, 3 pattern. So that works in capturing or calculating the distance along that segment. Now, if it's above that gradient, then it's a lot more complicated. Okay, it's the following morning. I kind of gave up on trying to explain this yesterday because I think I was a bit tired. I had to put my kids to bed anyway, so it was getting late. And I'm fresh now, can hopefully do a better job of explaining how this works. I suppose I'll start with the approach that I took. So this section here, so I'm talking about the section below this line, which is a bit more complicated than this other section, which is reflected in this code here. Now, how did I arrive at this solution? So what I did is I took that section and copy pasted out the underlying data from this origin, like a block of data like this, into a spreadsheet so that I could do some calculations. And I wanted to be able to express these values as a function of x and y, given that the deflection in the x-axis is this way and y is this direction. So I started just by plotting. Well, first of all, let's just make some observations. So you can see a pattern. 0, now we've got this local chaos anomalous value here, but in essence, it goes 1, 0, 1, 2, 3, 2, 3, 4, 5, 4, 5, 6, 7, 6, 7, 8, 9, 8, 9, 10, 11. So you can see that repeating pattern where the base is 2, 4, 6, 8, and then you've got an increase in the number by 1 for each group of 4. So I thought that was a good starting point. Let's just express this row. Now it's worth pointing out that every other row follows the exact same pattern, which of course makes sense because your knight can go from here and then to here, or it can go to here. So you can see the logic of why you'd have this pattern, at least for the base point. So expressing this line then as a function of x, started with just doing the values of x, 0 through 20. And because it's groups of 4, let's divide by 4. That gives us 0, 1, 2, 3, 4. We got these weird decimals. So if we take the floor of that, then we get 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, etc. So multiplying by 2, then we get 0, 0, 0, 0, 2, 2, 2, 2, 4, 4, 4, 4. So this now captures the base of that group of 4, which is a really good starting point. So now just calculating modulo 4 of n gives us 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And you can probably see where I'm going. If you now add those two together, we now get 0, 1, 2, 3. And now we have this 2 area, and it's now adding on the modulo, so it's 2, 3, 4, 5. Similarly, 4 here with the 4 base, you've got 4, 5, 6, 7, 6, 7, 8, 9, 8, 9, 10, 11. So that now captures this line perfectly with a mathematical expression. But we've got these pesky in-between lines. So every odd number in the y-axis, we have some different behavior. So I think I started off with a ternary that just implemented a different set of logic for odd y values, but that evolved actually into something that is just a little bit neater. I started initially by just trying to shunt this whole thing over by 2 if we are on an odd y number. This actually explains that better. So I've got 0, 1, 2, 3, 4 just going up in the y direction, and I've got modulo 2 going 0, 1, 0, 1, 0, 1. So that gives us a means that we can target the odd rows. Multiplying by 2 gives us a offset. So 0, 2, 0, 2, 0, 2. So if I was to just add this to n, that offsets the value that we calculate. So that takes into account the y and will offset in the x direction by 2 if it's on an odd row. I've got this row linked up to the y value here that I can change. If I set that to 0, yeah, you'll see that this top row here is just n. And if I put a 1 in here to make it odd, the whole thing just shoves over by 2. Now we can apply this logic that we had before on top of this now shunted over version of n. I've called it yn just to differentiate it from this n. It's not y multiplied by n, just to make that absolutely clear. But essentially, I've copied the same formulas and I'm doing the exact same thing, taking the floor of yn over 4, timesing it by 2 to get this grouping. Now you'll see the grouping is now offset by 2 in the x direction, which is what we want. Modulo 4, and summing those together, we now get these groups of 0, 1, 2, 3, 2, 3, 4, 5, 4, 5, 6, 7, 6, 7, 8, 9. Now, the problem is these are starting at 1 rather than 0. This is starting at 3 rather than 2. This is starting at 5 rather than 4, etc. So we need to add 1 if it's on an odd row. So that's just as simple as adding on y modulo 2. And with that, we now have the expression for the segment that I was trying to express as a function. And you'll see if I change this back to a 0 again, it now recalculates and is for an even row. Changing it back to some odd number, it shoves it over and targets a odd row, which again, repeat. So coming back to the code, that's exactly what this is doing. It's, yeah, kind of hard to read, but that is basically what it is doing. In fact, it's exactly what it's doing. So there we go. That explains that line of code. The only final thing to point out is just we've got some exceptions here that account for the local chaos that I mentioned. So if dy plus dx equals 1, then in that case, we are immediately adjacent because the sum of the x and y deflection is 1. The only possible place that can be is adjacent. So in that case, we just hardcode a 3. If the dy and dx values are 2, then we always return a 4 because it is always 4, which is exceptional. And there's one other scenario. Now, everything I've done up to this point has been for an infinite chessboard. Now, there is an exception, a single exception on a fixed 8x8 or any size chessboard, actually. If your knight starts in the corner, then there's no way for your knight to get to this square in 2 moves, because if you imagine a chessboard, to get here on this infinite chessboard, we can hop off the board and back to the 2. But that's just obviously simply not possible on an actual chessboard. So in order to get here, it takes 3 moves, I think. Maybe it's 4 moves. Yeah, it must be 4 moves. Yeah, there. That's right. Easier to show on here. So in order to get to there, you must go here, 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 and then back here. There's no other. There's probably a few variations of that, but there's no. If you could jump off the board and then there, then that would be great, but you can't do that. And with that, I can proclaim a mathematical solution to this problem. So I'm just going to do an attempt. And it passes all of the tests. Very pleasing indeed. Now, of course, this isn't the 2-liner. I'll just grab that one now. It's essentially the same, but compressed down. A lot of these things cancel out. I think I managed to compress some of this logic down a little bit, but it's the same logic. So here's the 2 side by side. This is the 2-liner just spread over multiple lines. And it extracts out some common themes into variables, like this is repeated here and here, for example. Does that a few times. You use dy plus dx a few times. And I've simplified this down, but it's essentially the same. Math.floor replaced with this. And yeah, I think I just reordered the exceptions to be at the end. In fact, I think I discovered that the exceptions are always 2 greater than what it would have been. So rather than hard coding specific values, I'm just checking if it is an exceptional case. And if it is, then I'm adding on 2. So I'm doing this, which will resolve to a Boolean true or false multiplied by 2, which will therefore end up as either 0 or 2 based on whether this is true, and just adding that on at the end. And there you go. That's the 2-line version, and I will attempt. And it passes. So that's it. So thanks for watching. I hope you enjoyed. If you haven't already, please subscribe, and I will catch you on the next video.